And it all kind of kicks off with this warning, right? We've all seen it. Objects in mirror are closer than they appear. So what's the deal? Is the mirror lying to us? To figure that out, we've got to get back to basics and understand the fundamental rules of light.
And that leads us straight to our very first big idea, the law of reflection. Seriously, think of this as the one single unbreakable rule that's in charge of every reflection you've ever seen. Doesn't matter if it's in a tiny puddle or through a giant telescope.
The easiest way to picture this is to imagine a single ray of light, like a tiny billiard ball. When that ball hits the mirror, it bounces off at the exact same angle it came in at. Simple, right? Angle in, angle out. Now, to get a bit more precise about this super predictable bounce, physicists have a couple of key terms we need to know.
Okay, first up is the angle of incidence. All that is the angle of the light ray that's coming in. But here's the little catch. We don't measure it from the mirror's surface. We measure it from an imaginary line called the normal. Just picture a line sticking straight out from the mirror, perfectly perpendicular at a 90-degree angle. That's the normal.
And you guessed it, on the other side of that normal line, we have the angle of reflection. This is the angle of the light ray as it bounces off the mirror. Again, measured from that same normal line. So you've got your angle coming in and your angle going out.
And all of this brings us right back to the law itself, which is just beautifully simple. The angle of incidence is always equal to the angle of reflection. Or, if you want to be nerdy about it, I equals R. That's it. That one elegant little rule explains everything. Your bathroom mirror, the reflection in a spoon, even the massive mirrors in the most powerful telescopes on, well, off the planet.
All right, so that's the rule for just one little ray of light. But the image you see of yourself isn't one ray, right? It's billions and billions of them all hitting the mirror at once. So what happens when they all come together to form the image we see in a regular old flat mirror?
Here's the mind-bending part. The you that you see in a flat mirror isn't actually behind the glass. It's an illusion. What's really going on is your brain is getting tricked. See, your brain is programmed to think that light only travels in straight lines. So, when light rays bounce off the mirror and hit your eyes, your brain traces them backwards in a straight line to a point where they look like they came from. This creates what physicists call a virtual image. It's a perfect illusion that seems to be sitting there, right behind the mirror.
And the images you see in these flat or plane mirrors are super predictable. They have a consistent set of rules. For one, they're always virtual, meaning they appear behind the mirror. They're always upright, you're not upside down, and they're always the exact same size as you. They're also laterally inverted, which is just a fancy way of saying left and right are flipped. That's why writing looks backwards. And finally, however far you are standing from the mirror, your reflection appears to be that same distance behind it. This is our starting point, our baseline for how reflection should work.
Okay, but this is where things get really interesting. What happens when we just throw that flat surface baseline out the window? What if we take that flat mirror and give it a curve? Well, that's when mirrors stop just showing us a simple reflection and start actively bending and manipulating the reality we see.
So, you've basically got two main ways you can curve a mirror. You can make it bulge outwards, that's a convex mirror, or you can make it curve inwards, that's a concave mirror. The absolute easiest way to remember this? Just grab a spoon. The back of the spoon, the part that bulges out, that's convex. The inside of the spoon, the part that would hold your soup, that's concave. It goes inward, like a little cave.
And you wouldn't think it, but that tiny difference in shape has a massive impact on what light does. A concave mirror, the cave one, with its inward curve, basically gathers up light rays and focuses them all down to a single point. It converges light. A convex mirror does the exact opposite. Its outward curve takes light rays and spreads them all out. It diverges light. And this one fundamental difference is the whole reason they create totally different kinds of images.
So, how in the world can we predict what we're going to see in one of these curved mirrors? Well, the good news is we don't have to guess. We can actually draw it out. We can map the path of the light rays using a really simple but super powerful technique called ray tracing.
And here's the best part. You don't need to trace a billion rays. You only need to draw two very specific, very predictable ones to find your image. Rule 1. A ray that comes in parallel to the mirror's main axis will always bounce off and go through a special spot called the focal point. Rule 2 is just the reverse. A ray that first passes through the focal point will always bounce off and travel out parallel to the axis. And wherever those two reflected rays cross paths, bam! That's exactly where your image is going to form.
Now, before we can draw, we just need to know the layout of the playing field, the basic anatomy of the mirror. We've got the principal axis, that's just the main center line.
We've got the center, which is the center of the giant sphere the mirror was sliced from, and then we have the focal point, that special spot we talked about, which is always exactly halfway between the center and the mirror itself. Once you know these key landmarks, you can predict literally any reflection.
Okay, so drawing these diagrams is awesome for getting a feel for where the image is going to be. But if you need to know exactly where it is, down to the millimeter, well, for that, we need to turn to math. And don't worry, it all comes down to one surprisingly simple equation.
This is it, the mirror formula. It's this beautiful little relationship that connects three key things. F, which is the mirror's focal length, U, which is how far the object is from the mirror, and V, which is how far the image is from the mirror. The magic of this is if you know any two of those, you can always figure out the third.
Now, there's just one tiny thing. To make sure the math works out, we have to follow a few simple rules about positive and negative signs. Think of it like the rules of the road. We just have to agree on which way is which. So, for real objects, the distance u is always considered negative. For the focal length f, it's negative for concave mirrors, the focusing ones, and positive for convex mirrors that spread light out. And finally, for the image distance v, if your answer is negative, it means you have a real image in front of the mirror. If it's positive, you've got a virtual image behind it.
Okay, let's take a breath. We've covered the basic law of reflection, we've talked flat mirrors, curved mirrors, we've even learned how to draw the rays and do the math. We have all the tools we need. So now, let's go all the way back to the beginning and finally solve that mystery.
And the answer is, it's the shape. That side mirror on your car, the one with the famous warning, is a convex mirror. It bulges outwards, just like the back of a spoon.
So why on earth would they use a mirror that messes with our perception? Well, there's a huge safety benefit. Because it bulges out, it gives the driver a much wider field of view. You can see more of the road. But there's a trade-off. Remember what we said about convex mirrors? They always create an image that is virtual, upright, and this is the crucial part, smaller than the real thing. And that's the key to the whole puzzle. Your brain operates on a very simple, very ancient rule. If something looks small, it must be far away. So when your brain sees a tiny version of a car in that mirror, it instantly thinks, oh, that car is way back there, even when it's right next to you.
So get this. The mirror isn't lying to you at all. It's actually showing you a perfectly accurate reflection based on the laws of physics. It's just that the image is smaller. The warning label isn't there because the mirror is faulty. It's there because of a glitch in our own human brains. It's a warning about how we interpret the truth that the mirror is faithfully showing us.
And that really makes you think, doesn't it? If just by curving a surface, we can so powerfully change how our brain perceives reality, what happens when we take the next step? What happens when we stop bouncing light and instead start bending it as it passes straight through something, like a lens? Well, that is a whole other story.